Okay, so here's where we were last time. Reminder, just sort of the big strategy that we're taking here in chapter 15 is that we're finding that there's a bunch of theorems that all kind of follow the patterns of the fundamental theorem of calculus, viewed appropriately, right? So we viewed the fundamental theorem of calculus as a statement about a computation of change, not integrals. Integrals are how we compute change, not vice versa. So it's a seemingly backwards point of view. But viewing it as a computation of change, viewing change as an accumulating quantity, and writing that accumulation as an integral, and then interpreting its integrand as a density. Right? So we found that you can take that point of view on the fundamental theorem of calculus. And then we sort of ran with that point of view and came up with several alternative sort of theorems that come out of just applying that same point of view to different contexts. So the fundamental theorem of line integrals, R2 and R3, same. Right? I mean, different details, right? But morally, big same idea. Green's theorem, significantly different context, very different domains and quantities in question but structurally though it's all the kind of the same ideas. We have an accumulating quantity. It's not change anymore. Now it's circulation. Nevertheless, it accumulates over a two-dimensional region, and et cetera, et cetera. And what we're seeing now is the same kind of thing, but in a three-dimensional context, and we end up with Gauss's divergence theorem. Which can be written in several different ways. I'm circling this one arbitrarily. But the idea is, given a three-dimensional region, you could talk about its outward-oriented boundary flux. You think of that outward-oriented boundary flux as being something that's computed on the boundary surface. I suppose that's true, but very importantly, that outward-oriented boundary flux accumulates over the solid itself, can be computed with a triple integral, and there is this associated notion of density, divergence. So in the same way that, it seemed a little silly at the time, but I made the observation you can interpret the derivative as change density because of its position in an integral. Well, analogously, sort of by extension, we're going to interpret the divergence here as being flux density, because this is the density that comes up in an integral computing flux. Okay. All right. Now, so we've talked through that a lot from different point of views. We've seen the algebra. We've seen the diagrams. Reminder, here's the diagram picture of Gauss's divergence theorem. If you have a vector field and you compute its divergence, if you have a solid and you look at its boundary surface, right, then the flux of the vector field over the boundary surface, the triple integral of the divergence over the original solid, same thing. All right. So I want to give you a sort of a different point of view now, just kind of drawing some pictures. I think that I put this document, this PDF document, on Sakai in the resources section. It is possible that I might have thought I did but didn't. So anyway, I guess I'll try to remember to check that after class. But if you go to Sakai and look for this document and it's not there in the resources section, please let me know and I'll make a point of putting it in there because I want y'all to have a copy of this too. Okay, so anyway, I want to draw a picture of this accumulation concept in the fundamental theorem of calculus. Now, hopefully this is a picture you've kind of had in your mind, but I just want to get it down on paper. Here is a function that you see over the course of this interval from a to b. The value of the function changes from that value to that value. Okay, now we're looking at a graph. This is the one of these pictures that I can draw where I actually can draw a graph, so try not to get bogged down in the specifics of the fact that this is a graph. This is just a tool for visualizing what's going on. Okay. All right, but I want to talk about this change. We have a change happening. We measure change as a simple formula. It's f of b minus f of a. We look at a value of the function here. We look at a value of the function here, and we subtract. Or as far as the domain's concerned, we look at the value of a function here, and we look at the value of a function here. Those are the points in the domain where we're looking at the values of the function to compute change. So the computation of change happens on the boundary. Sure, of course it does. How sensible. Right? That's the easiest way to measure change. Look at the starting value, look at the ending value. Okay. But now let's ask this question. Is that really where the change happened? Well, no, don't be silly. Right? I mean, look at the curve. This curve is showing you that the values of this function slowly changed all the way over the course of this interval. Right? I measure the change on the boundary, sure. But that's just a measurement. That's just where it's convenient to do the calculation. Where did the change actually come from? Well, it comes from, gosh, I feel weird repeating myself. The change comes from where the function is changing, right? I mean, of course it is. This is, dare I say, obvious. So this part of the domain, if you will, that's where the change is actually coming from. That's where the change is actually happening. Yeah. Okay. All right. Okay, so we measure the change on the boundary, but altogether the change is really an accumulation of little changes that happen over the domain. Now, as it turns out, there's not much change happening aside from on this general vicinity here, but nevertheless, it's an accumulation over the interior. Now, let's talk about how much change is happening where, and this is a little bit awkward. If I want to say, for example, how much change is happening at this point? Well, at that point, the function only has a single value. We really talk about. Wouldn't make sense to talk about how much the function's changing at a point, right? What makes sense is to talk about maybe in the vicinity of that point, how much change is happening per unit distance, right? So I could talk about, on that little piece of interval, I could talk about change per unit length. So how much of that measured change is happening over that little piece of the domain? Okay, and so that's very naturally recognized as a density because it's accumulating quantity. How much of the accumulation happens per unit size? Accumulating quantity per unit size, that's a density. And then, side note, hey, as it turns out, lucky break, this is something we happen to recognize. That's the derivative. Well, that was convenient, right? But anyway, so be it. Okay, all right. So the reason I want to talk about this business with the fundamental theorem of calculus is this is the perfect sort of template for a similar discussion that I want to have about the divergence theorem. I want to go through this exact same series of observations, just not about change accumulating over an interval, but about flux accumulating over a region. Now, I made an artistic choice here. Please forgive me. It's just really, really hard to draw pictures of three-dimensional things, right? But even worse, it's hard to draw pictures of three-dimensional vector fields and surfaces, and especially when the vector fields might be going every which way. I mean, this would have been a terribly, terribly ugly picture if I had drawn it three-dimensionally. So I'm drawing it two-dimensionally. So, if you will, use your imagination to extend this to 3 dimensions. I'm just going to draw sort of the two-dimensional version of it. Okay. All right. So we have a flow. Well, we have a vector field, and I'm interpreting the vector field here as representing the flow of a fluid, etc. Note that this vector field is not constant. The vector field is short over here, and the vectors are long over here. Okay, we'll come back to that. We have a boundary of this region. We're looking at this region here in the middle. That region has a boundary. The boundary is that green. I'm going to say boundary. I mean, keep in mind. I mean, it looks like a curve. That's because I'm drawing a two-dimensional picture. But if this were a three-dimensional picture, we'd be talking about a solid. So we've got that boundary. Remember, also boundaries are oriented outward. And I could reasonably ask the question of, what's the total flux through this boundary? And how would you compute total flux? Well, of course, you would compute the flux on the boundary. Just like here, you compute the change on the boundary. Well, of course, that's the easiest way to do it, right? And so, you might even say you perceive the flux as happening on the boundary. That's where you measure it, right? And now let's do a very quick calculation, sort of back of the envelope, sort of order of magnitude kind of deal. How much flux are we actually getting here? Well, along this edge, there's no flux. The fluid is going parallel to the boundary, not through the boundary, so there's no flux there. Likewise, there's no flux over here on this edge. Right? There is some negative flux there. I say negative because, of course, the vector field is going inward. Orientation on a boundary, being as it is a boundary, is by definition going outward. Okay, so a little bit of negative flux over there. What about way over here? Well, over here, look how long these vector fields are. These field lines are really long. There's a large, this time, positive flux over on that side. Right, so a little bit of negative flux on one side, a lot of positive flux on the other side. Grand total, what does that add up to? Don't forget a couple of zeros on the top and bottom. Grand total, that adds up to a significant amount of positive flux. Right? Okay. All right. So if we were to think of this vector field here as representing the flow of a fluid, there's a lot more fluid flowing out than there is flowing in. Okay. All right, so positive flux. Does that mean that somehow on the edge over here that there is a spontaneous generation of fluid that's happening right there at that edge? Well, no, of course not. I mean, in the same way that change doesn't happen here at the edge just because that's where I measured it. That was the positive term in the calculation I did on the boundary. So that positive term, that must be, this is where the change happened. Well, no, of course not. That's not at all how it works. Change is an accumulation over the entire domain, right? So very analogously, here, that's not where the change, that's not where the flux happens. The flux happens somewhere inside. Right? Okay. All right, now let's go back over to here. Where is it happening on the inside, and how do you get your hands on that? Well, we made this observation that you can sort of look down at the small scale, and you can look at, what's happening, on a given little piece of the domain, and you can look at how much change per unit size is happening on this little piece, and you can kind of piece it together. And we ended up, details aside, noting that the derivative is a way of telling you per unit size how much change is happening in a general vicinity. Right? The derivative is telling you, it's not telling you change, it's telling you change density. Right? Well, we can play an analogous game here. And let me zoom in so I can draw better pictures. Let's look at a little region over here. Drawing my little outward-oriented boundaries there. So there's a little region, and its boundary, outward-oriented. And let's think about the flux. How much flux is happening on that little piece, right? We've got this total accumulation of flux. We know there's a positive flux. How much of the flux is happening there? Well, here's the thing. Not unlike what we were just seeing on that top piece, the flow is along the boundary, not through the boundary. So there's no flux on the top. There's no flux on the bottom. There's a certain amount of flux on the left side, and there's a certain amount of flux on the right side. The flux is negative on the left side because the orientations are opposite. The flux is positive on the right side because the orientations are not opposite. So again, we have sort of a plus and a minus, and how do they compare? Well, you got to look at these field vectors, and look at these field vectors. Oh, in this whole area over here, the intention of what I had drawn was that those field vectors are all the same length. So what we have on this piece here, on this tiny little piece, here, there's no flux happening on the boundary of that piece. There's flux in and there's flux out, but it's the same amount with opposite signs, and they cancel, and there's just none there total. Yeah.
Is this supposed to be like a cube in 3D?
Yeah. Everything is. Yeah, I'm drawing 2-dimensionally, but supposed to be 3-dimensional, just for sort of artistic. I think the idea is, well, even though it's dimensionally unrepresentative, I think the visual convenience is worth that little sacrifice. Yeah. So you're quite right. And again, my apologies, but again, I think it's a good trade. Okay, so there's no flux happening there. Just like you come over here to this picture, how much change per unit size is happening over here? Well, there's, over that run, there is there's no rise. There's just no rise at all. So there's no change happening there. You might say the value of the function here and the value of the function there are the same, and when you subtract, they cancel. Very analogously over here. Well, the vector field over here, the vector field over there, they're the same. And with the orientations, you end up kind of subtracting and they cancel. The analogy is very strong. And you can make that argument everywhere over here. So same argument there, same argument there, same argument there, same argument here, same argument there. I mean, everywhere, as long as the field vector is doing what I have drawn kind of on this left side over, there's no flux happening over there. Same thing over here. Now this comes as a surprise. Feels like there's something very different. Look how long these field vectors are. Now I have, am I in blue? Yeah. Longer field line going out. That's more positive flux. But I also have longer field line going in. So it's more positive, more negative, still zero. Still adds up to zero. Let's look at, again, this applies everywhere in this region. Large positive, large negative adds up to zero. Zero, 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 zero. There's no flux happening anywhere on kind of the right side of the picture either. Where's the flux happening? It's happening over in here. Let's see, let me get back to pencil mode here. So let's look at that little region. Well, there's flux in. There's the field lines are maybe a little longer than they were, but they're still kind of short. Now, just a little further over to the right, the field lines are a little longer, right? Notice that these field lines are kind of increasing in size. They're short over here, and then maybe a little longer, and then even longer as you sort of move to the right. So on this edge, the field lines a little stronger than they are over there, and as a result, there's just a little bit more positive flux than there is negative flux. Right? And so grand total, there is a little bit of flux that's happening on this piece that has a little bit of area. Well, size. Volume. Don't forget this is technically 3-dimensional, right? So on that piece of a certain size, there is a certain amount of accumulating quantity of flux. There is a certain amount of flux per unit volume happening in that piece. And now the details, I can't draw the pictures of the details as easily here it's very easy to see how in the limit that's going to give you a derivative. Lucky break. Derivative happened to be this familiar quantity, right? So we could just see, oh yeah, in the limit. So the derivative is our change density here. More details involved here. Not going to be able to draw those details, but I claim if you'd like to know, how much of the, per unit size, how much of the flux that we're measuring on the boundary is actually happening in that general vicinity, per unit size, of course. Divergence computes that for us. Straight out of Gauss's divergence theorem. So, going back to, where we started from, we measure the accumulation, we measure this accumulating quantity of, I'm in the wrong mode. Sorry. We measure this accumulating quantity of flux on the boundary. Sure. Is that where the flux is actually happening? Nonsense. The flux is happening in here. As dictated by what divergence computes, right? However you compute the divergence, that's telling you, in a given region, per unit area, how much flux is actually being created in that space. Everybody see what I'm talking about? So now, again, the more algebra to fill in some blanks in this Gauss's divergence theorem picture, but the ideas, the structure of the argument is the same in both cases. Okay, so I think this is a really useful point of view. I think this is very important for intuition. By the way, we kind of skipped over this discussion when we were talking about Green's theorem. Real quick, let's talk this through regarding Green's theorem. Now, this really is a two-dimensional picture, right? Green's theorem. So here's our picture. We have a region with a boundary curve. Don't forget, boundary curves come with an orientation, like so. And we can talk about circulation on that boundary. The circulation on that boundary, well, you measure that on the boundary. Sure. It's still an accumulating quantity, though. That circulation, you measure it on the boundary, but you can look at tiny little regions in here, for example, and ask, well, how much circulation actually happens here? Understanding orientations go the way they go. Right? And it's a nice exercise. I'm going to let you all think this through for yourselves. But I claim that on that little region there, the vector field is constant, and if you look at the four different pieces, two of them are going to have 0 line integral, the other two are going to have exact opposite line integrals. Grand total, there's no circulation happening on that piece, or on that piece, or on this piece, or on this piece, or there, or there, or there, or here. Sure, there's more flow happening down here, but that doesn't mean there's circulation. On the boundary, as you go around the whole thing, it's just bigger things canceling. There's still 0 total circulation. But in here, that's where circulation's actually that's the circulation that you measure on the boundary, where it's really coming from, where that circulation's happening. Places like that, right? Where just to fill in a couple of lines, where the negative circulation is small and the positive circulation is greater. So there's a little left over after the subtraction. Okay. All right. Okay. Like I say, I think this is a really nice picture. I'm a big believer in analogies, learning by comparison. So I hope you will look at what you understand about the fundamental theorem of calculus. This point of view, again, try to nurture this point of view on the fundamental theorem of calculus as a computation of change, as accumulating over an interval. Think of it in that sense. The more you can understand that, then the more opportunity you will have, by extension, by analogy, to have a comparison point for understanding what's going on with Gauss's divergence theorem and why we call divergence flux density. Okay, all right. So that's enough of that. Let's go back to our notes. Here we were. Did all this stuff, did this example. I want to talk about some applications to physics today. So let's think about fluids. We were just looking at some pictures of fluids. Right? We're thinking of this perhaps as a fluid flowing around. And flux represents flow of the fluid out of the region. So flow of the fluid. Right? So looking at this picture, there's more fluid flowing out and less fluid flowing in. In grand total, there's a positive, exodus of fluid that we're seeing here. Okay. All right. So, well, where is that happening? What's really going on there? Don't forget, flux represents quantity per unit time. Outward means that we're looking at how much that quantity is decreasing inside, right? Just think about the sort of the pluses and minuses of it. If you have a certain amount of quantity inside, if there is a positive exodus of that fluid, then the total amount inside is decreasing. Okay. All right. I throw this K in here just as so I don't want to have to worry about units. Right? And the vector field represents fluid flow in what sense, and that's not what we're interested in. So the K is to ignore those issues. So, divide by volume on both sides. Flux per unit volume is flux density is divergence. Right? Divide by volume. So per unit volume. When you divide mass by unit volume, you get density. So here's just in the context of thinking about vector fields representing fluids, you could interpret divergence as representing how fast the density, the fluid density, is decreasing at a certain point. Right, and let's go back to this picture. I think that kind of makes sense. How fast is the density decreasing, kind of generally speaking, over here? Well, there's just as much stuff going into that region as there is going out of that region. You wouldn't expect the total quantity of stuff, or per unit size, the density of stuff in that region to be changing. It's just there's just as much stuff going out as going in, but not so here. In that general vicinity, there's a lot more leaving than there is going in. Right, a little bit going in, a lot leaving. Well, just think about, if this was a fluid of, bird migration or whatever. Well, there were a certain number of birds in this general vicinity, and a lot of them are leaving, and a few of them are entering as they pass through. But if there's more leaving, more going out than there are going in, number of birds is decreasing. Okay. Yeah.
Does the thing eventually run out of birds then?
Yeah, so we're thinking here about at an instant, rates of change that are happening just at one moment. Now you're quite right, eventually you're going to run out of birds. Yeah, and so the fluid flow will eventually change. Right? This is not a what was the old parable about the cup that just keeps spouting the wine or something? I forget. There's some old parable. Yeah, eventually you run out of birds. Quite right. Yeah. So this is just describing a momentary, at a certain instant, what is happening at that single time. And eventually, so for example, let's think about this scenario. Eventually all the birds have gone all the way east, and the flow at that point is just zero. Absolutely. Right. Okay. Here's a different point of view that you can take on fluids. It depends on the situation, but you draw this. Let me draw a picture. Let's look at this picture here. Draw a picture like that, and you could reasonably ask the question, hey, what's that a picture of? And you could take the point of view of, there's a mass exodus happening here. There were a bunch of birds in there, and they're running, screaming away from maybe a cat, parachuted in and landed right there at that spot, and the birds scatter every which way. Bird density then decreasing away from the cat, something. Right? But what if this were a steady state situation? What would that mean? Hypothetically, right, where there's fluid just constantly, continually just flowing away from a certain region. How could that be? The suggestion would be that, okay, if we sort of jettison the idea that, we're keeping track of how densities are changing. Let's assume we're looking at a steady state. So densities are constant. If there is fluid flowing out of a region and yet the quantity of fluid is not changing, it's got to be being replaced somehow. So there must be, whatever this fluid is, whatever this vector field is representing the flow of, there must be some of that fluid spontaneously generating in some way on that piece. So here's a silly example. Let's think about a two-dimensional example. Imagine a slab of concrete, and imagine it's raining. Right? Well, there's water, so there's going to be a certain amount of water flow, but as it rains, wherever the high point is on the slab, the water is going to be kind of just continually flowing away from that high point. Are you going to eventually run out of water? Well, not if it's raining. If it's raining, if there is a source that, water can keep reappearing right there on the slab, well, then that source of water, however much water is coming down onto the region, that's how much water is going to be flowing out. And so here, picture like this, when flux is positive, we call that a fluid source. And you could imagine an analogous sort of flipped picture where, what if the fluid was doing like this? Well, golly, there's fluid flowing into this region, and yet it's not filling up. How could that be? Well, it must be spontaneously disappearing, and very nice comparison to what we all see in the kitchen. You could think of this as a sink. It's a fluid sink. There's fluid flowing into the region, but since it is not accumulating, it must be disappearing down the sink. Okay. All right, so these are just a couple of physical metaphors. If you're really talking about how fluids flow, in reality, there could be sort of a combination of things going on. There could be a source combined with a changing density. And so it gets a little bit more complicated. It's mostly a matter of notation and keeping track of what things represent. But these are kind of the two big sort of points of view, competing points of view, combinations of which might apply to a given circumstance. Okay. Alrighty. So moving along, let's talk about physics a little bit and talk about gravitational fields. I'm quite sure you all have heard of gravitational fields. You may recall we wrote down this formula for a gravitational field some time ago. There was a homework exercise where you were asked to compute the divergence of, well, I think they wrote it a little bit differently at the time. I think they wrote it as kx over magnitude of x cubed, which is just different constants, but morally equivalent. Okay. This is not exactly the formula for gravity that you saw in high school, but it's not contradictory. This cube is not does not mean that this is an inverse cube field. This is inverse square. Again, we've made this observation before. I could rewrite this as negative gm over magnitude of x squared times x over magnitude of x. Right. This then is just a unit vector indicating direction. That thing has magnitude equal to 1. So in terms of the magnitude of this field, this magnitude is inverse square. Right? So don't fall for the little illusion there in the denominator. Okay, so that calculation that y'all did back in section 15.1, you computed the divergence. The divergence was 0. That is away from the origin. Well, yeah, of course. Look at what's happening at the origin. At the origin, the magnitude of x is 0, and this vector field is undefined. And so there's a catastrophic explosion of discontinuity that happens at the origin. So at the origin, all bets are off. But away from the origin, the vector field is perfectly well defined, and the divergence is 0. Okay. All right. So it turns out there's a lot of really powerful consequences of this. And I'm going to show you how to argue a couple of these. We don't have time to go through all of the observations I want to make about physics here, unfortunately, because it's a fun argument. But let's consider a situation where you have a region, three-dimensional region, right? And there's no mass inside of this region. There might be some mass on the outside of the region. Let's say there's some mass over here, right? And that mass outside of there is making a gravitational field. Oh, I better make these field lines longer. Making some gravitational field like that. And of course, it's shorter the further you get away. Okay, so we've got mass outside the region, but critically, no mass inside the region, and got a gravitational field that gets created, and I'm going to ask what seems like an intractably difficult question. What is the flux of this gravitational field through this boundary surface of this solid? And let's just take a moment to dwell on what a brutal calculation this would appear to be. The vector field is pointing in different directions at different places. It has different magnitudes in different places, and the formula is got not only square roots in it. Don't forget, magnitude is a square root. It's got square roots and fractions, right? Square roots in the denominator. So, not a nice looking calculation. Furthermore, look at how bumpy and wiggly my domain is. My domain here, let me get rid of that mess. My domain is curvy and stuff, and so really I'd have to parameterize this curve, this surface. Excuse me. Parameterize the surface. So it looks like it'd be a brutal calculation. So let's not do that, right? Here's the way we're going to deal with this. We're going to realize that because that surface is a boundary of a solid, I can rewrite this with Gauss's divergence theorem. We want to compute the flux. Fine. Flux, that surface integral of the gravitational field over the boundary of our region. Let's call this region R. The flux, that surface integral that I'm so scared of, is a triple integral over the region itself of the divergence of that vector field dv. I've got a triple integral over the region. In that region, the divergence is 0. I've got myself a triple integral of 0, and that's easy. The answer is 0. Isn't that nice? That's a really powerful idea here, right? So now, what makes this idea come through so strong? It's the fact that the divergence is 0, right? If the divergence had been some other weird, ugly function, then I would have, by arguing the divergence theorem, I would have turned an ugly flux integral into an ugly triple integral, and I don't know, maybe it's a little help, who knows? But it wouldn't be this massive conversation stopper that this is, right? The fact that the divergence of the gravitational field is 0 is extremely powerful. So this fact here, now let me, I guess I have to leave a certain amount of this mess, but the fact that the divergence is 0 is the key thing that allows you to draw several other conclusions. Not only is it the case that mass outside of the region is irrelevant to gravitational flux, you can also further argue that even with mass inside the region, it's still kind of good news in the sense that, and there's a whole argument here that I do have to skip, but we just don't have time to go through the argument. But mass inside the region, only the amount of mass matters in terms of flux. Where the mass is it all sort of compressed into a dense area, or is it sort of spread out, or is it a cloud, or how is that mass distributed? Who cares? Doesn't matter. Just a total amount of mass is all that matters. And you can furthermore work out exact formulas, and here it is. The grand total gravitational flux through a boundary surface is this really easy little formula right here. -4 pi gm. That's it. G being that gravitational constant in the vector field equation. It's just a constant, right? So flux is proportional to the mass that's inside of the region. This is a great formula to memorize. Please make sure to memorize this formula. It gets very useful in a lot of situations, and it's just so easy to memorize, right? For one thing, most of this formula is a constant, that flux is proportional to mass. That's an idea, not a formula, right? So definitely make sure you know that idea. So all you really have to memorize is, well, what is the proportionality constant? -4 pi g. Not that hard. Okay, divide by volume. Flux per unit volume gives you flux density, aka divergence. Mass per unit volume gives you density, mass density. Okay? And so what we have here is that if you have not a single point mass, but if you have a distribution of mass where maybe there's non-constant. By the way, this is how mass really works in the physical world, right? There are no actual point masses, right? Mass is distributed. I mean, there's a certain amount of mass in my stylus here, but it's not at a geometric point. That the mass in this stylus is distributed over a certain amount of space, right? So when you have a distribution of mass, the density tells you the divergence of the gravitational field. And this is a crazy cool calculation. Let's just kind of take a moment here. How, without this fact, without the observations through this argument that lead to this result, that again, I'm sorry to say we don't have time for, how would you compute the divergence of the gravitational field when you have a distribution of mass? It's unthinkable. You'd have to look at each little individual piece of mass and the gravitational field that it creates. There's lots of little pieces of mass. Each little piece of mass creates its own gravitational field. There's infinitely many little pieces of mass, each of which is creating its own different gravitational field. Just to write the gravitational field, you'd have to write down a triple integral of a vector field, just to get the gravitational field itself. And having done that, you'd still then have to take the divergence of that monster. I mean, wow. Right? That would be really, really hard. So, much nicer to just be able to say, yeah, it's negative 4 pi g times the mass density. That's awesome. Okay. This next page of notes we're going to skip. I put a lot of stuff into my notes that's kind of optional, that I do when we have time, and this semester we just don't. Let me just remind you of another thing. I mentioned this on the first day of class, but you can't expect that in class we're going to go over every single thing in the course, right? We don't have time, so I have to make tough choices about what are the ideas that I think you can get the most out of by my explaining it, right? And as opposed to what ideas are you perfectly capable of reading on your own, right? So with that in mind, so I'm gonna, some stuff that's in my notes, even if it is course relevant, I might skip because it's just not a good choice of time investment in class. Okay, this stuff is not that. This is just supplemental stuff that I like to include because I think it's neato. We're skipping this term, so you can just absolutely skip this page if you would like. You're also very welcome to give it a look. I do think it's kind of cool if you're curious, but you're not obligated. Okay, let's talk about electric fields real quick. Electric fields. Here's the formula for it. By the way, if you have not had a physics course, don't worry about it. We're not really going to do hardly any actual physics in this course. All you really need to know is that if you have a charged particle, charge is just a physical quantity, right? It's kind of like mass in a certain sense. It's a physical thing. I can't define it with equations. It's just a thing that is. So if you have a charged particle, that creates something called an electric field. And electric fields created by one charged particle interact with another charged particle to make a force between them. And it's either an attractive force or a repelling force, depending on whether they're the opposite or same charges. And that stuff we're not going to get into. That's not our problem. Right? Really, all you need to worry about is that charges create something called an electric field, and here's a formula for it. Okay. Now, this formula looks somewhat different from the gravity formula. Well, of course it does. This isn't gravity. This is a completely different physical thing. This is electric charges and electric fields. Gravity's it's a completely different concept, right? Okay. And yet, structurally, this looks awfully similar. Look at that. It's radial with the magnitude cubed in the denominator. So this is inverse square, just like the formula for the gravitational field is inverse square. Really, the main difference is that there are some different constants out front. And, when it comes to calculations that involve taking derivatives and multiplying by things, constants don't really do much. This is morally the same exact vector field. Just different constant. That's weird. This is a big tip, by the way. So those of you who will be in the future taking E&M classes, if you haven't already had E&M, or if you're going to take it again here at Duke, I am a big believer in thinking of taking big advantage of how much electric fields look just like gravitational fields. So any intuition that you have about what gravity looks like and how gravity behaves, that's how electric fields behave. Pretty much. Different constants, and with this one other little difference that there is such a thing as positive and negative charges, and you can have repelling electric forces. You can't have repelling gravity. I don't know if that's a good thing or a bad thing. Probably a good thing. It keeps us all on the surface of the Earth, right? But anyway, aside from that one little difference of pluses and minuses, structurally, electric fields look just like gravitational fields. Okay. And so there's a lot of consequences of this. For one thing, because this is up to a constant, the exact same vector field, guess what? Its divergence also in exactly the same way is 0. Away from where the charge actually is, of course, at which point the denominator is 0, the field's undefined, catastrophic explosion of discontinuity. But of course, all that stuff's the same. Okay. And you also end up getting an extremely long list of analogous facts. If you have a region that has no charge inside of it, then there is no flux through the boundary of that region. Just like with gravitational fields. To whatever extent there is charge outside of the region, who cares? It doesn't affect the flux on the boundary of the region. If there's charge on the inside, it doesn't matter where it is. All that matters is how much charge. Don't worry about the distribution of charges inside of a region, just how much charge inside of a region. And again, you get these awesome, powerful formulas for sort of punchlines. Grand total electric flux. So this is the flux through a boundary surface of an electric field created by some distribution of charged particles. Tremendously intimidating quantity to want to compute directly. Really nice little formula for it. It's just the grand total charge divided by this constant. That's again, it's just a standard physical constant. And likewise, divide by volume. And you get the divergence of the electric field is proportional to this thing that's lowercase Greek letter rho, which is charge density in this case. This does not mean spherical coordinates. It's there's only so many letters, right? So some of them get double used, and unfortunately, rho in this context means charge density. And it's very standard. Okay, so I think there's a lot of value in. So look at these facts about electric fields and electric flux, and then skip 2 pages back to the analogous facts about gravitational fields and gravitational flux. What you'll find is that they're crazy similar. They're morally the same results, just with different constants. And keep that in mind as you go through your E&M classes. We will pick up here on Friday. You'll have a good Wednesday. Oh, a quick reminder. I am sorry, but I do have to cancel my office hours today.